Okay, first, I'd like to thank the organizers for the invitation and for organizing this wonderful talk, a wonderful conference. It's indeed a great honor. So I'll give this talk on variable energy flux and energy exact relations in MHD turbulence. So, so these are my collaborators, Manohar Sharma, Shadab Alam, and Somdeep Chatterjee. Okay, so let's go to the next slide. So I just want to advertise this book, which I wrote. A lot of today's discussion is on this book. So first, let's do hydrodynamic turbulence. So I will focus on this energy flux ideas. So I just want to relate to hydrodynamics, like start from Kolmogorov turbulence. So this is the equation which everybody knows. So the idea here is that the force, this force is going to change the flux. So Kolmogorov theory says that the flux is constant in the inertial range, but J cross B force, like Ampere force or buoyancy force, all these can change the flux as well as the spectrum. Okay, so it turns out to be a pretty nice formalism. It's a variable energy flux formalism, and that is what I will try to relate. So normally we assume that kinetic energy flux is constant even in MHD, but it won't be constant. Okay, we don't have very large resolution simulation to prove it, but I will just try to motivate that indeed it will not be constant. So this external force will be a different thing for different systems. So like for MHD, it is J cross B, Hall MHD, J cross B. Like Rahul's talk, there was a coarsening there was some force because of passive scalar, the scale, not active scalar. The scalar was affecting the velocity field. So all this will affect the flux. So the basic idea is that we start with the energy equation in the Fourier space. So all of it will be in Fourier space. So the nonlinear term is this one, and we have the same force sitting here. This is the injection term, and in Kolmogorov theory, of course, we assume the force to be at large scale, which is only injecting energy in the large scale, not in the inertial range. But MHD will inject energy at the inertial range itself. Now, this term is responsible for energy exchange across various scales, and that leads to flux. So this is what is responsible for flux. For kinetic energy flux, for magnetic field too, we can write down similar equation, which I will do a bit later. But this term is what is responsible for the flux. And of course, we have the condition K equal to P plus Q. So this is a triad interaction with 3 wave numbers participating in this. And this is a dissipation term. In the inertial range, the dissipation term does not really do much. So one formalism which we developed over, long time back, which I just want to say here. So in fact, yesterday's talk by the chairman, I believe it is very useful to think of energy going from a given mode to another mode. So there's a wave number P to wave number K. We can compute what is the energy transfer. So this formalism helps in quantifying this, and is very useful. It's kind of behind this flux. So it's the imaginary part of K dot UQ and UP dot U star K. So we say that energy is going from UP to UK. So these are the two Fourier components, and this is called a mediator mode. It doesn't really give energy or take energy, but it's a mediating the transfer. It's dot product with wave number K. Okay, so it's a very useful formalism for all sorts of flows, including MHD, which I'm going to come to that in a while. Now, flux, of course, is defined in terms of the same mode-to-mode transfer formula. We can do it in more complex ways. Krekner did it in 1959, but we can rewrite this in much simpler way by this mode-to-mode transfer. So energy is going from P to K. So all the modes within this sphere, all the modes inside gives me energy to the modes outside. So the giver must be inside the sphere, and the receiver must be outside the sphere, and it helps a lot. This is not picked up. That's one reason why I'm emphasizing this part in mode with emphasis. Okay, now, so let's look at what happens when we have the forcing at all scales. Okay, so this is something which we have been doing it in recent times. So the flux will change as a result. Why? Because now please focus on this sphere, which is this yellowish sphere. Now there is a forcing inside. So this blue wheels are supposed to be forcing, some kind of fans, and there are dissipation as well possible, like Ekman damping can dissipate energy at all scales. So this is like Ekman damping, you may call, or viscous too has some effects, but it's negligible in the initial range. But anyway, this is some kind of dissipation. Okay, in liquid metal flows, it is important the dissipation is at all scales. So this term FLS, so this FK is the energy coming into the shell by forcing. So clearly, so this can be derived. It's very straightforward from the formula I just showed and from the energy equation, you can easily derive this formula, and we find that the flux will change. I mean, basically it's energetics. How much energy comes in and how much energy goes out. If we feed in energy in this yellow shell, then the flux in and out will be different, right? I mean, just simple pure energy argument. And so that's the basic idea. So this term is changing the flux with various numbers. Now the consequence is okay. So let's try to recover Kolmogorov theory before we go into variable energy flux. Let's recover Kolmogorov theory. What Kolmogorov theory does is it makes an assumption that large scale forcing is a large scale, so it doesn't do anything in the inertial range, and also dissipation is weak in the inertial range. So right hand side is 0. Okay, and that leads to 5/3. But in general, if there is a forcing in the intermediate range, like in fact Rahul's example, there is a forcing in the intermediate range coming from this scalar fields, and that I believe, okay, now I can make the guess, that I believe is this part, this kind of forcing. Okay, so here I'm forcing. So if I force it, then flux will increase with wave numbers. It won't be constant. And if flux increases with wave number, then there will be more energy than what is there in Kolmogorov theory. So a spectrum will become shallower. Okay, so that's assumption, that straightforward conclusion we can draw. And we drew something very similar for convection. Thermal convection has helped us a lot to resolve whether it's Bogdanov or Kolmogorov theory. So it gives us this kind of inputs. Now for MHD, I will show that here the energy goes from velocity field to magnetic field. Okay, so that's what J cross B term does. Now, in fact, so kinetic energy should steepen, or the flux should decrease with your number, and it should correspond to this regime, right? So here the J cross B force is going to take energy out of velocity field. So flux will not be constant anymore, but it will decrease with K. So that's what we have been looking for, whether it decreases with K or not. Okay, so I will show you that indeed there is some signature that it decreases. So, I mean, this is a very general formalism. It works in many systems, including convection. If there's force, then we can apply this idea. Now, in going to MHD turbulence, that is the focus of this talk. Let's see what are the fluxes. Okay. Now, equations are more complicated, of course. So we have this equation has been, in fact, discussed in the previous by the previous speaker. So we have this term which is coming from the J cross B force. Okay, so that is a magnetic coupling. That's velocity field is interacting with magnetic field. Now we have equation for B, and equation for B has these two terms. Okay, now this is the advection term, U dot rad U, and this is also advection term for B. Okay, now this is a term which is coming. I mean, this in fact is coupling with the U. Okay, so now let's write down the equation for the energy. Okay, now that's where we can see all these transfers. So energy equation, so kinetic energy equation will be like one term is that, It comes from the velocity field, and this equation, this term is responsible for U to U transfer. Okay, so there is a transfer from velocity modes to velocity modes, and U to U transfer, and this term is U to, I mean, this is B to U transfer. So this energy is increasing or decreasing. So magnetic field is feeding energy to you or taking energy away. So we just look at the sign, and that will tell us which way is going. It turns out the pressure field does not do anything. Pressure field just goes away because of incompressible condition. Okay, it just doesn't participate. The magnetic energy equation also has very similar form. So this is the B to B term. So this magnetic field gives energy to B to B term, and the next term is U to B. So this term is responsible for the dynamo. Okay, so I want magnetic energy to increase. Where is that? Where does it come from? And it comes from this term, which is in the nonlinear term. It was B dot grad U. Okay, so we can really construct in detail this energy transfers. Like for network of energy transfers is all in sitting in here. Now we can look at this in terms of flux. Now that was like how one mode is giving energy to another mode, but you can look at the flux. So we draw this sphere, wave number sphere, and look at how the energy is going from the sphere. Okay, so this is a velocity sphere. Now U to U transfer is, so now we have two fields. This is B field and this is U field. So this is energy going from U from all the modes inside the sphere to modes outside the sphere. Okay, so this is the usual Kolmogorov flux formula. Okay, this is exactly same as what happens in the Kolmogorov Fourier space. The formula is U dot grad U. But kinetic energy can also go to magnetic energy. No, I mean that is by interactions. So these are the two terms here for the modes inside the sphere. So these are the two terms which are coming here. And of course, large scale velocity field can also give energy to large scale magnetic field. So there are, I mean, all these arrows. In fact, you can see that there are 6 green arrows, and there are different energy fluxes. Well, five green and 1 red. So this is magnetic field, the magnitude to magnetic transfer. So magnetic energy gives energy to magnetic field, well, B to B transfer, and this is coming from that term U dot grad B. Okay, so that is this term. Okay. So we exactly know which term is doing what. So now, why do all this? I mean, you may say that this is no big deal, but it turns out it's very useful. And so large scale dynamos, so the usual idea has been that energy goes from, like, if you look at old papers, kinetic energy goes like this, then there is a small scale coupling, and then there is the inverse cascade. Okay, so that kind of picture has been made. But it turns out the real transfer for large scale dynamos, which we did many years back, is coming from here. So if Prandtl number is small, then most energy follows in this channel. Okay, around 40%, 40-50% energy large scale fields or velocity field gives to large scale magnetic field. So this is what is responsible for large scale dynamo. I mean, really large scale velocity field modes are giving energy to large scale magnetic modes. Okay, so we can derive this by computation, also by field theory. So I did some field theory, which of course is a bit more mathematical, but simulations clearly show that. Now we can also do small scale dynamo. So large Prandtl numbers typically show energy goes via this channel. Okay, so energy goes via this channel. So this is large scale velocity field, like small wave number, to small scale magnetic field here. So we see that this kind of phenomena in detail. So we can also look at locality and non-locality and stuff like that. So these are of course non-local, right? I mean, these are different scales. Now the question is, do this energy flux in MHD vary in the inertial range? Normally, in almost, well, in fact, myself thought that we assume that these fluxes are constant, right? I mean, in wave number space K. So does it change with K? Now, with the ideas which I just described in early part for Kolmogorov theory and modification of Kolmogorov theory, we expect that flux to change it in MHD as well. So this is a repeat of the old slide, So if there is a force, which is indeed the case. I mean, the J cross B force is there. So J cross B dot U. Okay, so we write appropriate wave numbers, and we find that this will indeed change the flux. And so we expect for MHD this kind of scenario for velocity field. Okay, so this for the velocity field, magnetic field, this kinetic energy flux should decrease with K. Now, so the top one is the Kolmogorov theory. I mean, flux is constant, it is going straight. But in MHD, some energy goes via this channel, but some energy goes to B, right? I mean, it just goes to B. And that is what dynamo does. We are feeding energy to magnetic field. So expect this pi u to decrease with K, right? I mean, so it's just energetics argument, nothing more complicated. And in fact, we predicted based on this idea that there will be drag reduction in MHD. So what I mean by drag reduction is that if I turn off the magnetic field, there will be certain friction force. But if I turn on the magnetic field, the structures will be more coherent and there will be less drag on the velocity field, like normal drag reduction. So this follows from this idea. Yeah. So since these two, I mean, I'm clubbing these two arrows into this is greater than 0, we expect pi u to decrease with wave number. Okay. So let's see whether we get some signature of that. So I'm not, I mean, I've been basically not doing very big simulations in our group on MHD at present. So we did basically 512 cube. It was done in a hurry. And let's look at what happens for the various fluxes. So there are 6 fluxes and total flux as well. Now, it just looks too complicated. But U to U is here, U to U, the red one. Okay. Now, this small resolution of 512 cube is definitely resolved, small resolution. Rahul expects 8,000 cube anyway, but this was done in a hurry. So you see the red one, this one, red one is coming down. In this region, the red flux is just dropping sharply. And U to B, I mean, this is U less to B less and U less to B greater. So where U less to B greater, these two arrows are going up. So when kinetic energy is going down, I mean, this red one, this one I just drew. So that is the time when magnetic energy is getting energy, okay, these two places. So kinetic energy is decreasing, but very narrow, but then it picks up again, okay, it comes down and picks up again. There's some more dynamics which we see if you dig deep, which is I'm not going to describe here. So there is a signature that the flux is not really constant. It is changing its wave number, even all these fluxes. Now, normally in the y-axis is a log scale, but here intentionally we are drawn in linear scale. This was simulation done by Manohar, Somdeep. So this is a linear scale, and we can see that we can see the variations. And some of them are negative. That means energy is going. The arrow is opposite, okay, compared to what I've drawn in the picture. The total energy flux, of course, is here is positive. Okay, total energy flux is positive. Now, great. So this is some kind of poor man's proof that kinetic energy, the fluxes are variable, and together, you see, I mean, there are lots of variation of these fluxes, but the total is approximately constant in the inertial range, which is pretty tiny for 512 cube, but it is reasonably constant in the inertial range. So there's of course a lot in give and take like in economics, but overall wealth is constant in some sense. Now, is there an exact flux? Okay, no, or sorry, these things are changing with the wave numbers, but is there an exact relation? Are there exact relations? So let's look at some of the exact relations. There are exact relations. Okay, so what do I mean exact relations? So this kinetic energy flux, as I said, is decreasing the number, right? I mean, because there's an exchange. But let's look at this region. Now, I may feed energy from magnetic field can push energy into that. Of course, if there's a negative thing, there will be the sign will be opposite. But see here, there's energy going from U to U. I mean here, and there's energy going from B to U, and both of them together should dissipate in the dissipation range. So what I've written it here, So this is Kolmogorov kind of flux, this U by U, and this is okay. Yeah, so this is going into B, right? This is going into B, this quantity, and coming from actually my notation is slightly wrong, but just this is the picture. Okay, so this is going there, and that should be equal to total dissipation, and we can verify that does it really happen or not. Okay, now in the picture I showed you, this is basically combination of these two arrows. So we can compute all this. Similarly, we can write down what is the flux coming into B. So what comes from U and what comes from B, it should get dissipated. So this is, we can draw these conjectures. Of course, all these are true for steady states. So it won't happen when it is changing with time, but under steady state, we expect these relations to work. And statistically, there will be errors, but if I do enough averaging, I should get this equality. We can also get equal how much energy I inject. Some of it goes into U to U, and some goes into that, right? So this must be equal to this plus that. Okay, so this is what we written here. So there are forces relations we can write. Of course, with combination we can get more, but we can get exact relations, forces relations. Now these are the numerical verification. So now this slide looks pretty tiny. So this is the first relation. Okay, so this is adding the pi U plus 2 of the energy coming from U to B. Okay, so this is there are two other fluxes, and so this was this U and coming from B to U, and these get dissipated. And in this region, in the inertial range, both of them match. So blue is the total dissipation, the blue line, and this is some of those fluxes. Okay, now the other arrows also in the inertial range. So this is supposed to work for inertial range. So we ignored the dissipation. So these are all working in the inertial range. The blue line is matching with the green line, and here red line matches with the green line. So it doesn't work for the dissipation range. Of course, we can also make it for dissipation range, but then we need to compute the dissipation and add to that, and then it will work. So these are exact relations we can write down, though these fluxes are changing with the numbers, but we can do that. Now, are there some fluxes which are constant in MHD? Okay, so U and B fluxes are pretty much changing with K, but there are fluxes which are constant in K, which are Elsasser variable fluxes. Okay, so pi Z plus and pi Z minus. These are constant. Why? Because there's no cross transfer. So there's an energy exchange in U and B, right? I mean, that's by J cross V force. But if you look at the equation for Z plus and Z minus, there's a nonlinear interaction, but the energy equation, if you write down the energy equation, the flux, there's no cross transfer from Z minus to Z plus and vice versa. Okay, so Z minus gives energy only to Z minus. Okay, Z minus to Z minus and Z plus to Z plus. We can show this very straightforward. I mean, there's not much trouble with that. Okay, of course, it's best to do it this mode-to-mode transfer. Okay, and it works beautifully. Now let's look at the fluxes. These two fluxes, pi Z plus and pi Z minus. This is the red line and the blue line. Both of them are roughly constant in the phi 12 cube in the initial range. Okay, and this is the cross-electric flux, which is also a constant. Total energy flux, of course, will be constant. Okay. Now, what good are these ideas? Indeed, I mean, there's some benefit of these ideas. So normally we look at energy fluxes and the energy spectrum for EU and EB, right? In the previous talk, we had focused on EU and EB, right? I mean, the speaker was talking about that one. Now, we know that fluxes are not constant. Pi U and pi B are not constant. They are changing with K. So they will show, like, for example, we expect, because U is losing energy, so expect it to be steeper, and pi B to be shallower than phi third. Okay. Of course, we can't really resolve here, but kinetic energy is definitely steeper than magnetic energy. Okay, that's what we expect from these flux ideas. But Z plus and Z minus, we believe, will be a better guide for spectrum because fluxes are constant. Okay, that's one conclusion we can draw from these ideas. Second, drag reduction. So as I said before, kinetic energy, if had it been purely hydrodynamic, then all the energy goes from U to U. I mean, this flux is constant in pure hydrodynamic. But if we put in magnetic field, then some energy goes from U to B like that. And so this flux is less. And that leads to less flux means less drag. Okay. Now this argument given in the paper, which is shown there, and we should verify it using simulations, and we did find there is some truth to that. We didn't have, of course, pipe, but we did in a box, and we did work out all right. In polymers too, exactly the same thing happens, and that's the connection with MHD. In polymers, instead of B field, you can just put a polymer, and there's energy going from U to polymer, and that leads to reduction in drag. Of course, these are ideas about bulk, not on the. I'm skipping the effects of boundary layers, but bulk does show this behavior. Now, in summary, we have the pi u and pi b are varying with k in MHD, but pi z plus and pi z minus are constant in k. Now, consequences on energy spectrum and the drag reduction. Okay, so these are the three references. This paper is still under review, so it has discussions on various fields, including polymers, convection, and Cahn-Hilliard fluid as well. So I did talk about Cahn-Hilliard in this paper. Okay, thank you. I will stop here, and I'll welcome any question or comments.